Welcome to the Agile Software Engineering Deep Dive, the podcast where we unpack the ideas shaping modern software engineering. My name is Alessandro Guida, and I've spent most of my career building and leading software engineering teams across several industries. And today I want to talk about something that sounds almost like science fiction. Self-learning machines. It sounds like a phrase from an old movie poster, where the computer becomes conscious, locks the laboratory doors, and politely informs humanity that its services are no longer required. But behind the dramatic wording, there is a very real engineering question. What happens when AI starts learning from itself? For years, generative AI has been trained on enormous amounts of human-created material. Books, articles, websites, documentation, code, discussions, images, videos, and all the strange, brilliant, messy, contradictory material that humans have produced online. But now the internet is changing. More and more content is generated, rewritten, summarized, translated, corrected, polished, or heavily assisted by AI. Some of it is excellent, some of it is mediocre, some of it is wrong, and much of it is plausible enough to be difficult to distinguish from human-created material. So the question is no longer only whether AI can learn from human knowledge. We know it can. The question is, what happens when future AI systems are trained on material produced by earlier AI systems? Does that create a powerful acceleration loop, where AI improves by generating new hypotheses, testing new strategies, refining its reasoning, and expanding what machines can discover? Or does it create a slow degradation loop, where models are increasingly trained on synthetic echoes of previous models, gradually losing contact with the richness, diversity, and unpredictability of real human experience? In other words, will self-learning machines become smarter? Or will they slowly start eating their own homework? In this episode, I explore why self-learning AI can be both powerful and dangerous, why examples from game-playing AI, reasoning systems, medicine, synthetic data, and scientific discovery matter, and why the real issue is not whether AI learns from AI, but whether the learning loop is grounded in reality. Because a bad loop says, generate, consume, repeat. A good loop says, generate, test, filter, learn, repeat. And that difference may become one of the most important engineering questions of the next phase of AI. Let's dive in.
Imagine for a second, right, that you ask an AI a complex question,
Okay.
and it outputs this incredibly detailed, highly articulate answer. But then, and here's the catch, it files that very same answer away, permanently incorporating it into its own training data set so it can, teach itself tomorrow.
Right, which sounds amazing at first, like a perpetual motion machine for intelligence.
Yeah, absolutely, a system that just gets smarter by talking to itself.
Yeah.
But software engineers and data scientists are starting to discover that this exact process might actually be a recipe for, well, digital brain damage.
Yeah, we are basically staring down this massive architectural crossroads. Depending on how we build the math behind that learning loop, it's either going to be the most powerful engine for discovery we've ever made,
Or what?
or it's just the slow, silent degradation of human knowledge.
Wow. Okay, so welcome to today's deep dive. We are unpacking issue number 32 of the Agile Software Engineering newsletter. It's titled, Self-Learning Machines, What Happens When AI Starts Learning from Itself?
It's a fantastic issue.
It really is. We're going to be looking at the core mechanics of recursive machine learning, digging into the data architecture, and pulling from their highly curated reading list to kind of figure out where this is all heading.
Because it really affects everyone.
Right. Whether you're a senior back-end engineer writing, deterministic code, or just someone using language models to parse a PDF, this evolution is fundamentally shifting the digital ground you walk on.
It is, and to understand the gravity of that shift, we have to look back at how machine progression actually functions. I mean, the concept of software improving itself isn't totally new, right?
Right, like Ray Kurzweil's vision.
Exactly. Kurzweil talked about this years ago, the idea that technology accelerates exponentially because, well, better machines build better machines.
Yeah, but the underlying architecture of how that happens has radically transformed.
Oh, completely.
Like if we contrast those architectures,
Yeah.
for decades, traditional software engineering was just deterministic logic. A human developer writes a strict set of rules, defines the parameters, and dictates the workflow.
You write a function, the computer executes it. Simple.
Right. And if there's an edge case you didn't account for, the program just fails or throws an error. It's never dynamically rewrites its own core logic.
Well, no, it's totally static. But then we transitioned into early machine learning, right? Those probabilistic models.
Right, where we feed it examples.
Yeah. Instead of hard-coding the logic for, say, how to recognize a cat in an image, we feed the system a massive data set of human-curated examples. We give it the inputs, the expected outputs, and the model calculates the statistical weights to bridge the gap.
But there was a critical limitation there, which was the training data itself. The raw material still had to be manually generated, labeled, and validated by us.
Yeah, humans were the bottleneck.
We had to supply the historical records, tag the good outcomes, tag the bad outcomes.
Which brings us to the real leap, right?
Yeah.
True self-learning. And AlphaGo Zero is the perfect illustration of this.
Oh, I love the AlphaGo Zero example, because it didn't just learn faster, it eliminated us entirely.
Entirely. It didn't ingest a single human-played game of Go. It was initialized with nothing but the raw rules of the board.
So instead of studying our centuries of, recorded strategies, it just generated its own data set from scratch by playing millions of games against itself.
Yeah, self-play. And the way it updated its internal neural network during that self-play is fascinating. Every time it finished a game, it ran a backpropagation algorithm.
Meaning what, exactly?
Meaning a win mathematically strengthened the specific neural pathways, those probabilistic weights that led to those exact decisions, and a loss penalized them. So it continuously optimized its own architecture based purely on the friction of the game.
So it's kind of like, it's the difference between studying someone else's flashcards to learn a language versus being dropped in a foreign country and just figuring it out by interacting and failing.
That's a great analogy. You aren't just absorbing static data, you're experiencing the absolute boundaries of the system. But the reason that specific architecture yielded such incredible results, like literally shattering centuries of human tradition, is the nature of the environment.
Because Go is a game.
Exactly. Go is a perfect mathematical universe. It has an undeniably rigid rule set, perfect information on the board, and a binary 100% reliable win or loss signal at the end. The reward function is absolute.
There is zero ambiguity. But when we talk about generative AI, the large language models we're embedding into search engines and our daily workflows, they operate in the realm of human language and abstract ideas.
And language is definitely not a closed-loop board game.
No, it's messy.
Very. There's no mathematical win state when you ask an AI to summarize a legal contract or draft an architecture review. The reality of human communication breaks that absolute reward function.
Right, because if an AI outputs an architecture summary, it might be incredibly fluent, grammatically flawless, but it could subtly misrepresent how two microservices talk to each other.
Or it could be really persuasive but lack deep technical nuance. The signal is just noisy.
Which brings us to the core structural threat. Because historically, AI trained on a human-generated internet, right?
Right. Our code repositories, forums, literature, all the brilliant, messy human stuff.
But the internet is changing fast. It's rapidly filling up with synthetic AI-generated content, automated SEO, synthetic code snippets, machine-summarized docs.
Yeah, which guarantees that the next generation of models is inevitably going to train on the output of the previous generation. They're going to eat their own synthetic data.
Okay, wait, I have to ask about the danger here. If an LLM is already highly capable and it outputs really articulate, well-structured text, why is it structurally dangerous for the next model to ingest that? Isn't it just reinforcing good grammar and clean formatting?
Okay, think about it like this. Imagine taking a highly detailed photograph and running it through a copy machine.
Okay.
Then you take that photocopy, put it back in the machine, and copy it again. Repeat that 50 times. What happens?
The sharp details blur into a gray smudge.
Exactly. The finest textures, the subtle shadows, they all wash out. In machine learning, this degenerative process is called model collapse.
Model collapse. So the AI is effectively engaging in self-amplified mediocrity.
Yes. Mathematically, it's a flattening of the probability distribution. An AI model naturally favors the most statistically likely sequences of tokens. It gravitates toward the center of the bell curve, the highly predictable patterns.
Right.
So when a new model trains on that generated output, the rare, complex edge cases at the tails of the distribution, they start getting assigned lower and lower probability weights until they vanish entirely.
But those tails are exactly where the most valuable human knowledge lives, like minority viewpoints or highly unusual software bugs or deep specialist knowledge.
Yes, all of that gets systematically washed out in favor of the safest, most generic statistical average.
Wow.
And the truly insidious part is that the syntax and grammar stay absolutely pristine. The output still looks incredibly authoritative.
So you don't even see the degradation on the surface. We're essentially building a hall of mirrors, artificial content reflecting back into artificial content, quietly stripping away the actual connection to reality.
That maps perfectly onto Melanie Mitchell's arguments. She's on the newsletter's reading list about what intelligence really entails. Just because a system outputs highly articulate sentences doesn't mean it fundamentally understands the concept.
Right. It's just mimicking the structural shape of understanding.
Exactly. And if it's only mimicking the shape of other synthetic outputs, it entirely loses the plot.
Yeah.
It also brings up Brian Christian's work on the alignment problem.
Which is what, exactly?
Well, if a model is self-learning from an increasingly polluted, flattened data set, its internal representations will mathematically misalign with the complex, messy reality of the human world it's supposed to operate in.
So if recursive learning inevitably leads to model collapse, does that mean all synthetic data is just fundamentally toxic? Like, are we hitting a hard ceiling here?
No, and the author of the Agile Software Engineering newsletter draws a brilliant engineering distinction here. Synthetic data itself isn't toxic. The danger is dictated entirely by how you engineer the learning loop. We have to separate sterile loops from productive loops.
Okay, so a sterile loop is the hall of mirrors we just talked about. Generation devoid of reality. The model produces text, the next one consumes it, the weird stuff gets washed out.
Right. But a productive loop introduces a critical architectural mechanism. Generation followed by rigorous evaluation against an external, meaningful constraint.
The machine desperately needs friction.
Yes, friction to test its hypotheses against.
So what does that look like in practice? The newsletter gives a few specific ways engineers are building that friction back in. Like, let's talk about reasoning systems, specifically STAR, the self-taught reasoner.
Oh, STAR is a great example. It avoids the trap by treating language generation the way a math student treats scratch paper. The model generates multiple different reasoning paths, step-by-step logic, trying to solve a complex problem. But it doesn't just blindly train on all its own generated logic.
Oh, it filters it.
Yeah, it only updates its weights using the specific reasoning paths that ultimately arrive at a mathematically or factually correct answer, verified by a hard external key.
So it's allowed to generate synthetic logic, but that logic has to survive the friction of a reality check. And if it fails...
If it fails, it's given the correct answer and forced to work backward to reconstruct a plausible path. It uses its own generation, but filters it through an absolute constraint.
I love that. So a sterile loop is like an echo chamber filled with yes men, but a productive loop is like a science lab.
Yeah.
Your hypothesis actually has to survive real-world friction. You're allowed to fail.
That is exactly it. Another fascinating approach to preventing degradation is token-level editing.
Right, because AI doesn't process whole words. It processes tokens, statistical chunks of characters.
Exactly. So token-level editing means the system isn't generating a massive synthetic document from a blank slate to train on.
So instead of writing a whole new article that might, hallucinate or drift toward the average, it acts more like a surgical editor.
Precisely. It takes a highly complex human-engineered dataset and selectively perturbs specific tokens. It might swap out a few variables, or alter a contextual parameter, or change the tone of a single paragraph. It acts as a controlled mathematical mutation.
Got it. So it preserves the messy human scaffolding, the real underlying ideas, but artificially multiplies the variation so the model has more robust edge cases to learn from.
Yeah, it's brilliant.
But I think the most profound example of a productive loop from the reading has to be the MIT glioblastoma study.
Oh, yeah. Applying reinforcement learning to medicine really shows the stakes here. Glioblastoma is an aggressive brain cancer, and obviously you cannot run exhaustive trial and error reinforcement loops on human patients.
No, you can't just experiment with dosing strategies on people.
Yeah.
So the researchers built a highly detailed clinical simulation model. They created a digital environment mirroring human biology and then unleashed the AI to explore different treatment schedules.
Right, and the goal was to reduce the toxicity of the drugs while keeping the treatment highly effective against the tumor.
And the engineering brilliance there is in the reward function, right?
Yes. The AI was given a dual constraint. It received positive reinforcement for minimizing the simulated tumor size, but heavy mathematical penalties if a toxicity score climbed too high.
And because it had the freedom to explore millions of permutations against those hard biological constraints, it didn't just default to the standard human assumption of, more medicine equals better results.
No, it actually discovered that in specific scenarios, administering lower doses at different counterintuitive intervals was far superior.
It successfully challenged human intuition, but only because its synthetic hypotheses had to survive the brutal friction of the medical simulation.
Exactly. If we pull this back to the macro view, Stuart Russell, another author from the reading list, frequently points out the control problem in AI. Building beneficial constraints isn't just a safety feature, it's the fundamental mechanism that allows a self-learning system to generate novel knowledge without just spinning off into noise.
So the dividing line between a degenerative hall of mirrors and a supercharged engine of human discovery is entirely defined by friction.
Yep. Which forces a massive perspective shift on how we treat data. If the machine desperately needs reality and friction, then data is no longer just, fuel we shovel into a furnace.
Data is an evolving ecosystem, and that brings up the most critical question in modern AI architecture. What is the teacher? In AlphaGo, it was the game board. In early generative AI, it was the human internet.
But if that ecosystem floods with automated, unverified content, then data provenance, knowing the exact origin, lineage, and verification status of a piece of data becomes the most important engineering problem of our time.
Absolutely. If you're managing massive data lakes, you can't blindly ingest text anymore. You have to track provenance. Was this human created? Was it an AI summary? Was it experimentally verified?
Max Tegmark discusses this too. What happens when systems aren't bound by slow biological evolution, but can rapidly design their own improvements?
And Pedro Domingos' work underscores that the algorithms themselves are only as good as the environment they optimize against. If we pollute the internet and our shared data, the models will mathematically degrade. It's a cultural problem now, not just computer science.
Yeah, every line of code a human verifies, every piece of complex documentation we author, every nuanced minority viewpoint we preserve online, it is literally shaping the evolutionary environment for the next generation of models.
We aren't just passive consumers anymore. We are the architects of the friction, which honestly brings us to a surprisingly optimistic conclusion from the newsletter.
Right, Kurzweil's accelerating feedback loop doesn't have to be a path to collapse.
No. A recursive loop accelerates whatever it's pointed at. It can accelerate noise, or it can accelerate discovery. The solution is engineering a shared loop. AI shouldn't substitute human intellect. It should amplify it.
AI models can explore massive solution spaces millions of times faster than a human brain.
But we have to inject the reality. We bring the creative intuition, the ethical constraints, the edge case curiosity. We define the reward functions and verify the outcomes against reality.
We act as the ultimate constraint. We create new foundational knowledge, and that verified human data becomes the grounded training environment for the next generation. They don't learn in a vacuum. We push them, they push us, and we accelerate together.
Provided we engineer the pipelines to preserve that friction.
Exactly.
There is an immense amount of technical nuance to these learning loops that we simply couldn't fit into this deep dive. To fully grasp the underlying architectures, you really need to read the full article.
Highly recommend it.
We strongly urge you to subscribe to the Agile Software Engineering newsletter. It's the best way to support rigorous, high-quality technical deep dives like this one, and their insights are absolutely essential right now.
It really is mandatory reading for anyone building in this new ecosystem.
So as we wrap up, I want to leave you with a structural question to think about. As AI becomes our primary interface for summarizing docs, generating code, and filtering the vastness of the internet, will we even possess the metrics to realize if the hall of mirrors has fully enclosed us? Or will that self-amplified mediocrity just slowly, silently become our new baseline for reality?
Thank you for listening to the Agile Engineering Deep Dive podcast. If you found this episode valuable, feel free to share it with someone who might benefit, a colleague, your team, or your network. You can access all episodes by subscribing to the podcast and find their written counterparts in the Agile Software Engineering newsletter on LinkedIn. And if you have thoughts, ideas, or stories from your own engineering journey, I'd love to hear from you. Your input helps shape what we explore next. Thanks again for tuning in, and see you in the next episode.